So now let's turn our attention here to example number 2. I actually would like you to try to work through all the questions here in example number 2 on your own to see if you can understand how to implement L'Hopital's rule in any of the cases where they might apply here. Now remember that L'Hopital's rule is not a one-size-fits-all rule that needs to be used in every single possible limit that we come across now. It only applies in certain instances. But you can go ahead and try to check here to see if it applies in these instances. So I'd ask you to go ahead and actually take a look at each of these. Pause the video right now, try to work through the answers, and then when you unpause, you'll see me work through the solutions. Okay, well hopefully you actually did go ahead and try to work through each of the questions that are here. Let's take a look at how we would work through them ourselves. So I'll notice here that at the beginning I have two nice differentiable functions, sine of x over x. Those are going to be good. And if I was to try to just directly substitute here, I would notice that I would get the form 0 over 0. So that's a good indeterminate form to make use of with L'Hopital's rule. So I'll start here by saying that I want the limit of, as x approaches 0, of sine of x over x. And by L'Hopital's rule, I know that that's going to be equal to a new limit, where again I just take the derivative of the top and the derivative of the bottom. Now the derivative of the sine is just the cosine, and the derivative of x is just 1. So I really just have here a limit, as x approaches 0, of the cosine of x. And this then should be equal to the cosine of 0, and the cosine of 0 is 1. So I get that this limit is 1. Now, I don't know how many of you may have noticed this, but actually back in section 3.5, when we talked about trig derivatives, we already established that this limit was going to be equal to 0. But one important thing to note here, the reason I bring this up, is that in that section, you can go back and take a look at it, but in that section it would have been very, very wrong for us to just state this limit here as the value 1. We had to go through a big complicated argument with we had like a big circle, and then there were like triangles coming inside and outside of the circle that we were using, and we were like comparing different areas. But we went through this big geometrical argument to determine this limit was 1, and we had to do that. The reason that we couldn't have used L'Hopital's rule in that section is that we didn't actually know what the derivative of the sine was. That was the whole point of that section back then. And so, although L'Hopital's rule is really powerful, it actually comes very, very late in the development here of calculus because it requires that I already know all of my derivative rules. All right, well, let's take a look here at part B. Let's see here. I'll notice that right away, again, I have two nice differentiable functions as I move out towards infinity. And natural log as I move towards infinity is going to be infinite. And same thing with our denominator here. So again, I have a good instance where I can go ahead and try to use L'Hopital's rule. So I'll say that my limit as x goes towards infinity here is going to be equal to another limit. Again, this is by L'Hopital's rule. And I'll replace my numerator with its derivative. And I'll replace my denominator with its derivative. So notice it's going to be 2 times and then 1 over 2 square root x. Okay, so this is starting to get a little bit messy, but notice that right in here you might have been able to take some simple algebra moves to clean all of this up. First off, I can notice that my 2's will cancel, and then I'm going to be left with a 1 over x over a 1 over a square root of x. I could go ahead, and again, just using algebra, I could multiply by the reciprocal and rewrite this as square root of x over x. And again, just using algebra and some basic exponent laws, I could rewrite this as 1 over square root of x. And so then I can see if x is going towards infinity, I'm going to get 1 over something infinitely large. It's going to be approaching 0. So there we go. I got 0 for this value. All right, for part C, again, I can go ahead here. I see that I have two nice differentiable functions as I move out towards infinity. E to an extremely large power is going to be growing infinitely large in size. Here I have a polynomial and only the leading term matters, so that's going to be moving out towards infinity. Again, a perfect time to make use of L'Hopital's rule. So here I have let's see, e to the 3x. I'm working with x squared plus 3x plus 5, and I'm going to implement here L'Hopital's rule. So this is going to give me a limit as x approaches infinity, and I'll take the derivative of the top and the bottom. Now, the derivative of the top here is actually just going to look like 3e to the 3x. Just got to make use of a little chain rule there. In my denominator, I'm going to get 2x plus 3. Okay, so this is a new limit that now I'm interested in working with, and I'll just completely forget that this limit here even exists. So let's see. Notice here that the top of this is going to be going towards infinity, and the bottom of this is also going to be going towards infinity. This then would be the perfect time to say I can figure out what this limit is by using L'Hopital's rule. Again, this new limit that we come up with is like an entirely brand new question, and I can use any approach that I want to figure out what its value is. Since it has two differentiable functions as x moves towards infinity being divided here, then I'm not going to have any issue with seeing that since it meets the appropriate indeterminate form, I'm good to use L'Hopital's rule again. So let's see. I can go ahead and replace this. See, there should be a 2 on bottom when I take that derivative. Up top, I'm going to leave the 3, and then I'm going to have e to the 3x times another 3, so I'm going to have 9e to the 3x. Okay, so there we go. There's my derivative. Now, all three of these limits have the same answer. So, as long as I can figure out this one, I'll know the answers to the previous two. But this limit, notice, is going to be moving in the direction of infinity on top and 2 on bottom. And so that's going to give me ultimately just infinitely large. So I would say that this original limit is infinite. So hopefully you were able to get these answers here to these questions. If not, hopefully I was able to clarify for you maybe where you went wrong or where you possibly had maybe just made a simple mistake. Of course, if you have any questions on this, by all means, please let me know, and we'll continue to take a look at more examples in the videos to come.